Hello, I'm excited to introduce our work, How Can Objects Help Video Language Understanding? Image-level embeddings and captions are widely adopted video representations in multimodal LLMs. Distributed embeddings are compact and expressive, while captions are interpretable and easy to use. But neither is designed to explicitly preserve structured spatial information at the object level. However, if we explicitly use objects to represent the video content, it can be expressive while interpretable. For example, in this basketball shooting video, the caption loses the position information of the ball and the hoop, making it impossible for the model to determine whether the shot will go in. If we accurately track the object's bounding boxes, we can infer the spatial relationship between the ball and the hoop and answer the question. In this project, we investigated two questions. The first one is how to adapt object bounding boxes to an MLLM, and the second one is whether objects offer extra advantages over distributed embeddings and captions. We thus design object MLLM to integrate visual embeddings, video frame captions, and object trajectories into one multimodal LLM. Object MLLM uses an object detection and tracking module to generate object bounding boxes. The object name and frame indices are sent to the LLM as natural language, and bounding boxes are adapted to language space using an adapter. We compare two types of bounding box representations and the corresponding adapters. The first, language-based representations, bounding boxes are treated as a string and use an LLM word embedding as adapter. In the second continuous representation, bounding boxes are treated as a vector and use an MLP projector as adapter. We compare these two adapters and show the performance curves with respect to the number of training samples. This shows that the language representation is more effective and also more data efficient than the embedding projector. Here, we break down the performance of the models on different types of questions. We find that the language representation actually improves the accuracy significantly on motion-related questions, like moving direction, moving count, and motion on perception test. Now we investigate whether the object tracking can offer extra advantages over visual embeddings and captions. We evaluate the performance of our model with different combinations of representations. Results show that caption and object bounding boxes together achieve the most competitive performance on most of the tasks. On benchmarks, especially requiring modeling relationship and interaction between objects, such as clever perception test, adding objects significantly improves the performance. Compared with existing models, Object MLLM performs the best across 5 video QA benchmarks. Our method can also generalize to richer visual elements. For example, we can represent human poses key points in language and feed it into LLM. We evaluate this method on human motion QA. The pose-based inputs outperform captions and synergize effectively with visual embeddings and captions. Here are two qualitative examples. In the first example, our model can tell the spatial relationship between the toy car and the table. In the second example, our model can understand the configuration of the objects. In contrast, the model with only captions as input fails to answer these questions. To sum up, we find that object bounding boxes can be integrated into MLLMs as a text sequence, which is more effective and data efficient than an embedding projector. Also, object bounding boxes are effective for spatial temporal understanding, being complementary to captions.